Thank you, Professor Consta. I'm Myrsini, and I'm from Wayne State University. And as Professor Consta said, today we'll discuss some results from a recent study focusing on enhancing the carbon sequestration in OPC concrete using recycled concrete aggregates and nanomaterials. As we all talk about today, concrete is responsible for a very large part of the global CO2 emissions, about 7 to 8%. So we all need to start doing great contributions into reducing that. With the growing demand of the construction materials in developing areas, we need to find ways to reduce this carbon footprint. Traditional concrete relies on natural aggregates, which is a very energy-intensive cement production. Both of those make great contributions to the environmental challenge. In the U.S. alone, the waste from construction and demolition product for the last year accounted for about 600 million tons of waste, not only from concrete, but also wood, asphalt, and metals. And only 40% of that percent is currently repurposed or reused, and leaves really high amounts of these potential materials, mainly concrete, to be reused and repurposed. By incorporating recycled concrete aggregates into concrete, or even substituting the whole amount of aggregates with recycled concrete aggregates, we could reduce the demand for natural aggregates. We could potentially lower the construction costs and also decrease the environmental footprint of concrete. As I show here, by completely substituting recycled concrete aggregates with natural aggregates, we see that we only have a 30% decrease in CO2 emissions, but we have to take into account that concrete consists of 60 to 70% of volume by aggregates. So that is multiplying, the effect of that is multiplying. In this presentation, this is the overview of the experimental process that we used in this research. We used recycled concrete aggregates. The first step was to implement CO2 on recycled concrete aggregates, or RCAs. And we produced CRCAs, which are carbon-treated recycled aggregates. Then we used these CRCAs to manufacture nano-reinforced concrete, and this went into a second carbonation process inducing CO2 to study the potential enhancement of CO2 capture of concrete. The materials that we used for this research were locally sourced. A company close by to our university is sourcing materials from local concrete structures, crushes them and cleans them in order to remove the debris. So we received the aggregates from them, and then we sieved the aggregates, and we kept the ones that we wanted to create the sieve analysis. So we didn't keep all the sizes that the manufacturer gave us. We just went through and figured out the ones that we thought that would be great to use. The problem that we noticed, and it's usual with recycled concrete aggregates, is that they have almost 1 order of magnitude higher water percent absorption. And that is due to their porosity, which is on the attached mortar around the natural aggregates. And that creates problems when we try to introduce those recycled concrete aggregates into the new concrete. In order to find a solution to make these RCAs better to use in our concrete, we went through this carbonation or carbon curing process. So the RCAs have attached old mortar in them. So we have the aggregate, the old ITZ, and the old mortar. We induce CO2 in this RCAs, and the CO2 inside the carbonation chamber reacts with the already existing products in the old mortar to create a calcium carbonate. So the technique that we use is this is a carbonation chamber. We thoroughly put the RCAs in there, and we induce CO2 for 24 hours. Then after that, we measure the water absorption, which decreased by almost 50%. We have also tried different carbonation times, and we observed that if we CO2 cure the RCAs higher than 24 hours, the water absorption reduction is not that high. So we only had marginally increases in water absorption, so we thought that there's no really good reason to increase this time higher than 24 hours. So what we did is we used TGA to analyze the attached mortar of the RCAs. And we observed that TGA of the RCA, and when we compare with TGA of carbonated RCAs, we achieved the CO2 uptake on the old mortar of the RCAs of about 3%. Now we wanted to see what is the results we get when we include the RCAs into concrete. So having the carbonated RCAs, we induce them into this new cement mortar mix and created a new concrete mix. So now we have a new mortar which is attached to the RCAs and a new ITZ. And we examined 3 different samples, so concrete with natural aggregates, concrete with RCAs that were not carbonated, and then concrete with the carbonated RCAs. Due to the difference in the water absorption, we also saw a difference in slump. And the way that we managed to combat this is to use saturated SSD condition natural aggregates and SSD condition recycled aggregates. What we saw is that our concrete with the recycled concrete aggregate has a 30% lower compressive strength when we compare it to regular concrete. But that was reduced to about 12% of lower compressive strength when the recycled concrete aggregates were carbonated. So we're not there yet to have a concrete with recycled concrete aggregates that has a compressive strength similar to what with natural aggregates, but we could use this as a not for structural concrete. In this slide, I'm showing you a projection of what would be the carbon percent, the CO2 emissions reduction with the different percentage of substitution of natural aggregates with recycled concrete aggregates. And we only observed a 15% decrease in CO2 emissions when our substitution was at 100%. That meaning we do have a lot of room to improve. And this is where we thought about using an additional material inside the new cementitious matrix, the new mortar, to achieve an additional CO2 uptake. As Marian discussed, titanium oxide have been recently really widely mentioned in literature that it can modify the CO2 capture. So we chose as our initial nanomaterial that that we're going to be inducing our new mortar to study the effect of the nano-titanium oxide. we disperse this nano-titanium oxide at an amount of 0.5% in water and added this in the cementitious matrix. We created concrete cylinders that after that we introduced into the carbonation chamber after 3 days of moisture curing. We follow the same procedure that Professor Gonsta previously described in her presentation. So we casted concrete cylinders, we let them cure, moist curing for 3 days, and then transfer those samples into the carbonation chamber. Applied a CO2% of 12% for the rest of the 25 days until the samples reach 28 days of age. Now, what we observed is that by having carbonated recycled concretes, the CO2 uptake increased about 2% compared to the plain concrete. The implementation of nano-titanium oxide inside the carbonated recycled concrete aggregate matrix gave us an addition of about 3% of CO2 uptake. We also examined the compressive strength of our samples, the moisture and the CO2 cured samples. Again, the carbonated recycled concrete gave us strength which is lower compared to the plain concrete strength, but what we saw here is that including nano-titanium not only brought the compressive strength up to the same concrete, the same strength, but also increased it. And when we compare carbonated recycled concrete with nano-titanium with the CRA concrete, we have an increase of 30% in compressive strength, while the carbonated materials in all three cases have a smaller increase in compressive strength compared to the moisture samples. Now, in nano-titanium gave us an additional about 50% increase in CO2 emissions. However, again, we do still have a lot of room to improve, and this was just one of the nanomaterials that we tried to include in the plain concrete matrix. So we next steps is to try different nanomaterials or different amounts of nanomaterials, and even replace our OPC with supplementary cementitious materials or other materials to even to increase this amount of CO2 emission reduction even more.